Hello, I want to look today a bit into observation models. So we discussed the recursive Bayes filter for state estimation and have seen that in this filter there are observation models and motion models involved. And I want to dive today a bit into basic observation models and explain how such an observation model could look like for a simple rangefinder, for example. So the goal for today is give you an idea how such observation model looks like so we can use it in different state estimation algorithms. So let's start. State estimation again was the task of estimating the state X of a dynamic system given observations and control commands. Observations typically referred to as Z and control commands typically referred to as U. And we have derived the recursive Bayes filter from that, which consists of a prediction step and a correction step. The prediction step in the recursive Bayes filter takes the previous belief and updates it with the so-called motion model into the predicted belief. So it's a prediction of where the system or in which state the system will be given the control commands that I assume to be known, specified with the U. And then a second step is the correction step, where we take the predicted belief and combine it through multiplication with the observation model into the corrected belief. So that means we are taking into account our observation to turn the predicted belief into the corrected belief. And this then is the end of this one iteration or one step of the Bayes filter. And we are here looking into the second part. So we assume to have the predicted belief and we need to multiply it with the observation model. So how does such an observation model actually looks like for a typical scanner? So the topic for today is getting an idea on how these observation models look like. Again, what does the observation model mean? It tells me what is the probability of getting a certain observation or the likelihood of getting a certain observation given I'm in a state. So given I am in a certain state, what is the likelihood of getting a certain observation? And we typically use this to take our current observation that we're actually getting and basically can specify how likely is it to actually get that observation that I actually got given that I'm in a certain state. And I want to start a bit with range sensors. So range sensors are sensors that provide you the distance to the closest obstacle that they are observing. This can be a standard 2D laser range scanner, as the 6 scanner over here. This is an Oyster 3D LiDAR, which provides you with 3D information. This can be a stereo camera or can be an active sensor which projects a pattern into the environment, for example, using infrared light, and then perceives the pattern with a camera, and through this information can estimate how far obstacles are away. So we don't really care right now which sensor we are using, which type of range sensor. And of course, if you have different models for different range sensors, they will have different parameters and different noise characteristics. We want to look here just into the most simplest form. And therefore, we stick here with this 2D laser scanner. So it's just kind of a laser array which is shot through the environment, and you measure the time it takes for the laser pulse to return, so a time of flight sensor, and you can then relate this with the distance to the obstacle by knowing how long the light has traveled. It could also be a sonar scanner, which does it not with light, but with an ultrasonic wave. So different ways how range sensors could look like. And we want to look into the very simplest form. So for now, let's stick with this type of range sensor. So these range sensors actually provide you in a single scan a number of range readings. So it's not just one proximity measurement, but actually a series of proximity measurements. Let's say every degree or every half degree you get a range reading. So then in the end you get a list of range readings or an array of range readings which tell you what the difference to the closest obstacle, and every entry in those rays corresponds to one direction expressed in the reference frame of the scanner. And so the question I want to look into, what is P of Z given xt for such a scanner? The first thing we do is we treat those individual measurements as independent measurements. So if a scan ZD consists of k measurements, we typically treat those individual measurements as independent given the sensor location. So not generally as independent, but independent given the sensor location and given we know the state of the world, given we know a map of the environment. That's kind of important that this is a conditional independence. So what it means is for our model P of ZT given xt, so I just added M here as a map to make explicit that we have information about the environment in the tasks we are typically referring to here. For example, if you have a map of the environment, an occupancy grid map, or a map of features, how can we build an observation model that we can use for localization? That will be one of those examples over here. And what we say is, we say all those beams are conditionally independent given that we know the state. So that means I can split, given that the scan consists of k scans, into a product of k elements and say what's the likelihood of that single beam, the single range reading, given the state and given the map of the environment. So this is the independence of the individual beam given the map, given the state information about where the system is, for example, in the environment for localization. Okay, so it's individual measurements are conditionally independent given the state of the world. So how does it look like in practice? If you have a range sensor here just visualized in 2D, so let's say this is the system where the location of the system, and those red rays here are range readings that I obtained or want to evaluate, and you can see some of those rays end up at the obstacle location, some actually seem to pass through an obstacle, and some lead to reflections or lead to objects which are closer to the system. And what we now want to do is we want to take this product over here and compute this value for each of those red rays and say how likely is to get that observation given I'm here and given that's what the world looks like. So you can assume you know where you are, you know what the world looks like, and then you need to answer the question, how likely is it to actually get that range reading? Or for laser scanners, so this is actually done, this is a sonar scanner over here, which is typically more noisy than a laser range scanner. For a laser range scanner, you would actually get something like this. So this is a laser scanner to the front and laser to the back. And these red things are rays at a very high resolution. And you need to answer the question, how likely it is to get actually that scan given that I'm at that point in the environment. And what this equation tells us that we can actually break it down and can only consider a single beam. So we take a single beam, one of those measurements, and just need to take care about the single beam, because in the end we can just combine them through that product. So assume we know where we are. We assume where the obstacles are in the environment because we know the map. What is a simple model for estimating how likely it is to obtain a certain range reading? And the most simplest form for that is a simple raycast model in these type of occupancy grid maps, so those maps that we have discussed already. So the simplest raycast model basically tells me what is the distance from the sensor location to the closest obstacle. So along the ray of light or the sound is basically in the line of sight to the next obstacle. And then say, let's add a Gaussian noise around that because this is assumed measurement noise. So we assume our sensor is here. This is where the obstacle is through the environment. So if I draw a line from the sensor through the obstacle, I need to estimate how likely it is to get a certain range reading. This is kind of the range reading, and this is the probability for getting it. And then it would be a Gaussian distribution centered around the expected distance. So there's something that we call also expected distance, because this is a true distance between where we are and where the closest obstacle is according to my map. So that's what I'm expecting to observe. And if I perform my range reading in reality, I will get something similar, but again, my sensor is not perfect. So there will be noise associated to this. And this is a simple raycast model that can perform this. So raycast, because we're basically tracing a ray in our map to estimate where the closest obstacle, given we know where we are. And this gives me the expected distance, and this is kind of a raycasting operation. And therefore, this is often called a raycast model, because I'm basically tracing a ray through my map until I find an obstacle. They are, however, more advanced raycast model than this simple model. Why is this simple model often not sufficient? The reason for this is that this doesn't cover all the things which could happen. So consider, for example, there is the wall, you're standing in front of a wall, but the wall is very far away, let's say 10 meters away, and you have a very precise scanner, let's say, has a standard deviation of 3 millimeters or something like this. So you would say how likely it is to measure a distance of 1 meter. And if the object is 10 meters away, small standard deviation or small noise in your sensor, how likely is to measure a distance of 1 meter? It's basically a probability of 0. But it can actually happen, for example, because a person walked through the environment and stands in front of your robot and obstructs the line of sight between the sensor and the wall. So you may argue, yeah, of course, violation against our assumption that world is static and all those things. But there's something that we have to deal with in reality, and if we don't take that into account, those systems will brutally fail. Therefore, you typically take into account additional factors than just this Gaussian noise when setting up an observation model. So this is an example for a more advanced observation model. So again, we have our predicted obstacle, so that's what the map tells us where our closest obstacle is. And then we have a function which looks like this with a little bit of a weird shape over here, or at least when you see that for the first time, you may argue, why should it actually look like this? So what is in there? So what we can see is there seems to be something like a Gaussian noise around the measurement being involved in here, which makes sense. That's what we have been using before. And having Gaussian measurement noise is probably something which is a reasonable assumption for most of those range sensors. But then there's something else involved. You can see there's a function which seems to be kind of decaying over here. Maybe there's some constant function over here, a constant value, and there's kind of a weird peak in the end. This peak in the end typically refers to something that we call a max range reading. And this is something, an invalid reading of the scanner where the scanner didn't get any return because the obstacle is too far away or may have been a reflection. So this is what's called this kind of invalid or max range reading. Therefore, it's shown here at the end. Okay, but the question is still, how do the other components come together? There's also kind of a small dent in here, which looks a little bit weird with something we don't see in a Gaussian distribution. So how do these things come together? And what this model actually is, it is a combination of 4 different models. So it's a mixture, a sum of 4 different models. And I want to go through those 4 different models and explain them how those models come together. And those models include your general sensor noise, the probability that dynamic objects you don't know about walk through the scene, a random component, and this max range component. So let's start with a simple beam-based proximity model. So this is kind of the model which just takes into account the sensor uncertainty. So this is basically the simple raycast model that we have defined or illustrated before. So this is the probability that of obtaining a certain measurement, so getting a certain hit. So this is the expected obstacle. Here is your sensor. So this is the distance to the wall, for example, in your map. And then the probability of getting a certain measurement can be described by this Gaussian distribution. And the mean of this Gaussian distribution is this expected measurement. You have the uncertainty of your sensor in here, and this is your Gaussian world model. So if you have a sonar, this variance is probably be larger than for a laser range scanner, or if you have a camera, it may again be differently modeled. If you have a range camera, so for example, there you would change that also with the distance to the obstacle, and this can be a complex shape, but for a given expected distance, this to be fixed, and then this would be one part of that model. So this is the pure Gaussian measurement noise. Then the second part we want to take into account is unexpected obstacles. How likely is it that an unexpected obstacle pops up, obstructs your field of view, and this way generates a different range reading from what you have expected. So this was my example of the person walking around through the environment. And this is often represented through an exponentially decaying function, which starts high, then decays, and stops at the expected measurement. And this is something which probably raises a lot of questions on your side. Why should we use such a model? Why does this model actually make sense and can be physically plausible or explained reasonably? Okay, so the first thing I want to look into is kind of this, the differentiation between are we closer than Z expected or not. And what you see in here, the function decays and then drops to 0 over here. And this leads to this dent in this combined function. So why do we have that weird thing? The reason is if we have obstacles, dynamic obstacles in the environment, we only care about those obstacles if they are between us and the obstacle we are expected to see. So if you're standing in front of a wall and a person walks by between us and the wall, we will see that person, so it obstructs our field of view. If the person however walks behind the wall, there's no way that I can see that person. So if the person is further away than where the map tells us there's an obstacle, it won't obstruct my reading, and it will not be sensed by the sensor. Therefore, it drops to 0 over here, and whatever happens behind the obstacles that are actually in the map I don't care. Of course, this may be different if you assume that some walls in the environment may be taken down, then this shouldn't drop to 0, but to a small value, but this is something that we ignore over here. So we are just taking this typical case into account that a person with dynamic obstacle walks or moves freely through the space, and then it's only relevant if it obstructs your field of view between the scanner and the obstacle according to the map. But why is it an exponentially decaying function? That's something that may sound weird or unexpected to you. But it makes sense to model it in that way, and it's actually something that it's a physically plausible model that you can explain very well. So let's dive into that and see how it looks like. So why do we have this exponentially decaying function to model dynamics? So what we do is we first assume a uniform distribution of these dynamic objects in the world. So we don't say they prefer certain locations. We just say, okay, they can occur anywhere with the same probability. If you don't have any further knowledge, that may be a reasonable assumption. Maybe we have some additional knowledge, then we could take it into account. But here in this general model, we assume that we have a uniform distribution of objects about the environment. But the key insight in here is only the closest object matters. So if you populate the space with a lot of people walking around, you're only interested in estimating the distance to the closest object and not to any object behind it. So if two people walking by, you're only interested in the first person, the one closest to your scanner, because this is the one obstructing your field of view, and the one behind it you don't care about. And so what we are then interested is kind of always having what's the probability of having a uniform distribution of objects in the environment, and then finding the first one. Then what we can do is we can actually draw an analogy to bit strings. How often do certain bit strings occur? So binary strings. And this actually helps us to actually come up in a very easy to understand way why this exponentially decaying function makes sense. So consider now we are in a 1D world, and I'm just kind of considering the distance between me and, let's say, the camera right now, or this may be the expected obstacle. So if I can randomly place objects in the environment, how likely is that a certain configuration occurs? And I'm only interested in getting the first obstacle. And we can, so 0 means a free space and 1 means an obstacle in this bit string notation. And the question is, how often do certain configurations pop up? So you can see this, the sensor is sitting over here and looks into this direction. And so the question is, how many configurations exist where the first bit string is 1 and all other bit strings I don't care about? Because I don't care if they're kind of people lined up or it's just one person. I'm only interested in the first person. So whatever happens behind it, I don't care. That's one of those situations where if you're measuring from here, the first object is the first person standing directly in front of the sensor and leads to a return. Then we can be in a situation that, let's say, there's some free space between the robot, free space, and the object. And then I can ask myself, how many bit strings exist with a 0 and a 1 and then followed by zeros? Because I'm again only interested in the first obstacle. And I can take that further, not only with 4 digits, I can take as many digits as large as my space is, and then count kind of, there's free space, free space, free space, object, and then there's, for example, the object in reality. Then this is a possible configuration. And the question is, how many of those configurations of all possible configurations in the environment can exist? There could be situations where there are no persons around. There could be situations around where there's 1 person around, 2 persons, 3 persons, 4 persons, 5 persons, and so on and so forth. I'm distributing them randomly over the space. Question is, how often do different configurations occur? So we can ask ourselves, how many bit strings exist? Let's say we have here 4 digits, 4 bit strings in this example, where the first digit is 1 and all others are 0. Or how many configurations do exist where there's a 0, 1, and then followed by 2 bit strings I don't care about. And so we can see how many bit strings actually exist with, different bit string exist with 4 digits. So how many are that? So if it's 1 digit, it would be 2, 4, 8, 16. So there are 16 different bit strings that exist, consisting of zeros and ones. So how many of those are these ones over here? These are actually bit strings where the first one is a 1, and then the others are all possible bit strings. So it would be 2, 4, 8. So there are 8 possible configurations where this can pop up. In this example, I fixed 2 of them, so there are just 2 times 2, 4 possibilities left. And here are only 2 possibilities left. And here's no other possibility left. So this is much more likely to occur than this configuration down here. So I can just count how often do certain bit strings actually occur. In this case, it would be a 1 because this one is fixed. There's only 1 configuration for that first bit. And then there are 2 possibilities for the second bit, for the third bit, for the fourth bit. So it would 1 times 2 times 2 times 2, 2 to the power of 3 equals to 8. And this for all the other bit strings. So I can see the point that it's much more likely to observe an object which is close to the platform than an object that is further away. In this example, even the probability that this is going to happen would be 50% of all configurations, so more than all the others here put together. Right? Because this is 1 plus 2 plus 4 is 7, and this is 8, so there are more situations where this will occur. And again, this is something where just count how often do certain bit strings occur, assuming this uniform distribution of an arbitrary number of objects through the environment. Then I will actually generate a pattern where it's much more likely to get a closer return than a return which is further away. And this is something which is modeled by this exponentially decaying function. Of course, I need to set up those parameters, and I can actually train those parameters by observing real-world situations and see how often does it occur. I will get different values in environments which are highly populated by humans compared to environments where no one is around. But I will get this exponentially decaying function. So this was kind of the second component of that model. Then the third component of this model is something we call a random measurement. Something completely random happens, something I haven't modeled at all. And everything has the same probability of happening. I just don't know what's going on. This could be a wall has been taken down and someone is walking behind the wall, or any other type of these weird situations. And we can just add a small uniform probability that the random event is going to happen, so that I can avoid that just because I haven't taken something into account, it drags the probability of model to 0 and then invalidate my whole scan. So this is just kind of the thing that something I haven't modeled, random effect. Let's take that into account with a small probability. And then there's a certain probability that we have a max range reading or no return reading. That depends if your sensor has a limited sensing range. Let's say it can only watch 2 meters far away and you have a large open wall, a hallway, then this is much more likely to occur rather than situations where in a very narrow space. You may have also other effects like a total reflection of the beam so that you get no return, or another error configuration of your scanner. So there's a certain probability, a constant probability, that this may also happen. If I now take those 4 models into account and sum them up, I will actually get this resulting mixture density function, which is with a small dent over here, with a small uniform probability, the max range probability, Gaussian, and my exponentially decaying functions. And this is how the resulting mixture actually looks like. And the question is, how can we actually determine those parameters? How do we know how much weight we give to the exponentially decaying function, and how much weight do we give to the Gaussian noise, for example? Because that's something that's relevant in practice. In the end, these are often different parameters. So if, in this case, for example, 4 parameters because of a weighted sum of those 4 functions, or maybe 3 parameters if I make sure I'm normalized to 1, so 4 parameters but normalization constant. The question is, how can we determine the parameters? Or how can we also determine the parameters like the width of this Gaussian distribution? Some of those parameters may be easy to obtain, like your measurement noise of the pure measurement noise, maybe something that even your sensor specifies, or you can determine this in a controlled experiment, putting your sensor in front of a wall and measuring that often enough and fitting a Gaussian distribution to that. That's something you can easily do. Other parameters like the exponentially decaying functions may be harder to obtain, and the weighting parameters as well. But what you can do is you can just use raw sensor data that you recorded in an representative environment and just learn those parameters from that data. So what you see here is a time series of a single range reading taken. So this is a time index, and this is the measured range, and this is basically distance of 3 meters over here. And so this is where my expected obstacle is. So I put a sensor 3 meters in front of the wall and take those measurements and record it. And this was an environment where a lot of people were walking by. And these are the results, how often you received a certain range reading. So what I can do is I can take this data. Of course, this only holds for an expected distance of 3 meters, and then fit my models into this. So the 4 components of this model will be fitted to that data. And I can do this, for example, with a histogram. So if I have a histogram here showing a range reading for expected distance of 3 meters or 4 meters, I will get these functions over here. And the curve over here is my parametric model, and the histogram over here is a number of occurrences simply counting from this data how often certain events have been taking place. And then I'm adapting the weight parameters that I'm as close as possible to that histogram. And you can see here that actually those random effects actually do happen. And of course, the more data you get and the more representative your environment is, the more probably some outliers here will vanish, and you will actually get very smooth models that you can learn from data. You can also do this for other sensors, such as not necessarily only for laser range scanners. You can use this also with sonar sensors. So sonar sensors are typically less accurate than a laser rangefinder. And if you take sonar scans, then you will get similar looking functions. The parameters may be different, but it turns out that even those sonars you can actually use with the same model and actually describe the observations that you're obtaining in an appropriate fashion. So that as a result of this, you can then, for example, for a certain observation that you're getting in an environment, so that's a real observation that you're getting, you can estimate where is this observation likely to occur. So P of Z given X and M, and you can vary X now because the observation is fixed, the map is fixed, but you can vary the pose. And then you actually get this example out here. And then you can see that the darker the grayish area, the more likely it is that you actually obtain this observation. So just by having this single observation, you can estimate that you're most likely in the corridor over here, and this is actually the true location. So there are a couple of locations which could explain that. So it's basically a system standing in front of 2 doorways where the door is open. This is something that occurs more often in this environment. But this is an example how you can use this model in order to estimate how likely it is to get a certain observation at a certain position. And this is kind of the standard or kind of advanced raycast model, which goes beyond just Gaussian measurement noise, and is a very popular and frequently used models in robot localization to interpret range readings and estimate how likely it is to observe the observation that we got at different positions in the environment or under different parameters. There's another model for those range sensors, which is called the Beam-Endpoint Model. So the Beam-Endpoint Model is an alternative model which is much simpler to compute with respect to the raycast model. So the Beam-Endpoint Model is a physically not plausible model in the sense that I'm only taking into account the endpoint of my scan and I'm ignoring if any obstacle lies on the path. The advantage is that this is a model which is extremely simple to compute, can be extremely fast and works surprisingly well, although it lacks quite some physical motivation. So the idea is as follows. You have a platform over here and you obtain a range reading, let's say here, 5 meters. And the question is how likely is that this occur? And the only thing that the Beam-Endpoint Model does, it actually checks the endpoint of that scan, says, is there an obstacle, yes or no? As easy as that. So in the most simplest form, you would just compute your sine-cosine operation to estimate the coordinate where that beam ends up. And then you say, is there an obstacle, yes or no? Of course, you now may not be very, you may want to take some noise into account here. So you may want to say, how far is this point away from the closest obstacle? So is it very close to a wall or is it in the free space? So this is something we are still very far in free space. This is probably a reading which would have a very low probability, but if the beam would end up here close to an obstacle, you can say it's actually more likely that I will get a return here. And the advantage of this model is that it can be computed very, very easily. So what you can do is you can actually build a lookup table which tells you where obstacles are in the environment. So this could be a lookup table, all the white cells are free cells, all the gray cells are obstacles, or what you can do is you can even convolve them with the Gaussian kernel or expand those obstacles and with a decaying function, and then estimate how likely it is to get a certain get a return at a certain point in time, given how far I'm away from an obstacle. And this can be computed very efficiently. So something as a Euclidean distance transform on binary images can be used to estimate for every cell or every pixel in an image how far it is away from a dark cell or a bright cell. And then this allows you to encode distance information in those cells so that when you get a measurement, you just have to look up one pixel, one element in the lookup table, and basically get your model parameters out, which is extremely efficient to compute and therefore a very popular tool, especially if you need to perform a lot of those evaluations. So localization systems such as a particle filter, which we will get to know later on in that course, they often use those models because they have to perform a large number of those evaluations. So if you, for example, have this as your lookup table and you then want to estimate the probability of getting a certain measurement here along that path, then this would be your resulting model. You're basically looking into bright and dark cells, which gives you a certain probability that a measurement will occur given where you are and what the environment looks like. So this is the probability of getting different range readings given the position that you're standing here in the map of the environment. So it's basically the probability distribution along that ray over here. But if you want to evaluate it, you know already the distance, because you know what you have measured, then you just need to look up this function at one specific point. And therefore this can be done very, very efficiently. So this is an example how an occupancy grid map can be turned directly into one of those so-called likelihood fields, or Beam-Endpoint Model, or likelihood field model is also a commonly used name. So you basically take your occupancy grid map and you're basically for every cell estimating the distance to the closest obstacle with the Euclidean distance transform, and then squeeze it, for example, through some Gaussian decaying function, so that in the end you get a kind of a smeared variant of this map here, just plotted in the inverse to have dark representing low probabilities, bright representing high probabilities, so that in this likelihood field, if the platform is at a certain position, you just need to compute the endpoint location, look up in that map, and the brighter the value, the better it is. Return your likelihood value for that observation. And again, that's something which is very efficient and therefore especially used on mobile systems where efficiency matters, or where a lot of those likelihood evaluations need to be performed. For example, when you're using Monte Carlo methods, where as particle filters, where this has to be done very, very often. Before coming to the end, I also want to look a bit into models for landmarks. So if you have distinct points, features, or landmarks in the environment, and how does a simple model look like for estimating a feature location in the environment, or having a feature location from your map and want to estimate how likely it is to get a certain observation. So one thing we can do is so-called range bearing sensors. So this is a sensor like as a laser rangefinder, which gives you a bearing and a range reading, because typically it's a rotating laser in this scanner and provides you range readings at different orientations. And then we're basically extracting from this range scan landmarks that we can detect in those scans and then have certain landmark locations. So we can write this down in parametric form if we assume a Gaussian noise, for example, a Gaussian, either a general Gaussian or a Gaussian in the rotational part and in the range reading part. This depends how I'm actually modeling it. But what I have a range bearing observation, so my range and my bearing information. I have an x, y, theta, my pose information, and maybe I have the observation of the landmark given a map. Then I can easily compute what I'm going to observe, so what I'm expected to observe. And this is kind of the distance between where the platform is, the pose, and the landmark. So this basically, where's the landmark according to my map? How far am I away from this? And this is just the Euclidean distance. And in which orientation it is something that I can directly determine using the etan2 function, so the arctangents, and just need to subtract my orientation of my platform, which tells me where I should see the obstacle. And this is then my mean estimate, and then I add some Gaussian noise to this. So this would be the simplest model that I can use this to estimate where I am. And a similar model, not exactly the same model, but a similar model can be used if you want to localize with landmarks, and has been done, for example, in the context of RoboCup. There's Robo-Soccer competitions where you also need to estimate the position of the platform with respect to some poles. And in these examples, there were 3 poles, 1, 2, and 3, and we get this range bearing observations. And then if you observe the landmark number 1, which is this one over here, basically these are the possible locations where you could be, taking into account a range bearing model, not exactly the same what I've showed before, but a similar one. Then for observing the landmark number 2, you will be something on that circle, which is represented over here, and the landmark 3 will tell you you're somewhere located on that circle over here. And by combining these informations about the different landmarks, you will get an estimate that you're somewhere over here, which actually represents to the position of the platform in reality. So by using multiple of those landmark observations, even if they don't allow you with one single observation assess the full state of the system, through the combinations of multiple those distributions, you're actually able to nail down where you are. So this is one of the examples by Dieter Fox on localizing robots on the soccer field for some early RoboCup competitions. We can also see what happens if we have a bearing-only sensor. So if we can only estimate the orientation but don't know how far it is away, this is then something you would probably have in a camera, or just kind of here as a kind of 1D line camera. Then your observation is just the bearing information, the heading information, but we know where we are, where we're looking to. We know where the feature or the landmark or the 3D point, depending how you call it, is in the world. And then the model becomes very simple. It's just basically in which orientation should it be, minus where I am, and then that's the location where you should actually observe your landmark. And then you may add some Gaussian noise to this with covariance in this bearing measurement. And this would be a simple model for perceiving landmarks or points in the environment. Here in the 2D case, but of course easily generalizable to the 3D world information. With this, I'm coming to the end of today. I just wanted to give you a short introduction how typical observation models look like that we can use in the Bayes filter framework for performing state estimation. Again, short reminder, because it's so central to a lot of state estimation problems. The Bayes filter was a recursive state estimation technique that allows you to estimate the state of your system at time t, given you know t minus 1, and uses for that the observation model and the control model. We looked into their different realizations, how this could look like, how it will be implemented in practice, particle filters, Kalman filters, extended Kalman filters, and other types, histogram filters, other types of state estimation techniques. And they often use one of those models. And today I presented a few of the observation models, examples for observation models that I used, especially with range sensors, where you want to estimate what's the likelihood of an observation given I know where I am and given what the world looks like. And we presented the simple or standard basic models that you can use today. You can go more advanced if you know a lot of properties of your sensors. You can, of course, put more efforts into estimating the proper sensor parameters. So if you want to calibrate a terrestrial laser scanner and you want to be super precise, you will probably take a different approach than the one I have presented here. What we've presented here are models for sensors we typically use on mobile platforms that we need to evaluate on a regular basis or very often in order to perform state estimation, where we want to have a compromise for simplicity of the model and still a good way for dealing with the, let's say, problems we have in the real world, such as dynamics being around imperfect maps, and those models have been very successful used in this context. Further reading, I still recommend the Bayes filter if you want to get an idea why you need those models, and especially the chapter 6 in the probabilistic robotics book on observation models is the chapter to inspect for the things that I've presented here today. So thank you very much for your attention. I hope you get an idea how those models look like that you use, especially for range sensors in state estimation algorithms. Again, if you use cameras or features, landmark maps, just the last 2 or 3 examples should give you an idea how that could look like. Typically that boils down there to a Gaussian estimate, for example, in your pixel coordinates, which is equivalent to the bearing information if you have a calibrated camera. And that's how you do that for point measurements. If you have those grid maps, it's a bit more complicated, but I've shown it here today. You may need to pre-compute your models, but typically what people do, they build lookup tables so that in the end they can be computed in a very efficient manner. So that's it. Thank you very much for your attention.